Hello everyone, I am Aryan Vaseem and my enrollment ID is BT20HCS108. This is part of my Introduction to Information Security assignment, and the topic that I have chosen for the research paper is Revocable Certificateless Public Key Encryption. First, I will give you a brief introduction to this research paper. So, let's begin with the introduction. Firstly, this research paper is authored by Sung So Sai and Yu Min Singh. So, public key encryption is a crucial part of secure communication and is widely used in various applications such as email, online banking, and e-commerce. Traditional public key encryption schemes have a certain limitation, such as a need for public key infrastructure or PKI and the risk of key compromise due to the use of public keys. The text in this research paper starts by discussing traditional public key systems. The text in this research paper starts by discussing traditional public key systems or PKS, which use certificates to map identities to public keys, which require a public key infrastructure to manage certificates. Senders can encrypt messages to receivers using their public keys, but certificates must be verified to ensure they are valid. Using certificate revocation lists or CRLs to check whether a public key has been revoked. The text then introduces identity-based PKSs or IDPKSs, which derive a user's public key from their identity information, eliminating the need for certificates but creating the key escrow problem. The certificate-based PKS or CBPKS is then introduced as a solution to the key escrow problem, where a certificate acts as a decryption key. The certificateless PKS is introduced as a further development of the IDPKS, where each user's private key consists of partial private key and a secret value, which eliminates the key escrow problem. Moving on to the next slide. Certificateless public key encryption or CLPKE is a promising alternative that addresses some of these limitations by eliminating the need for certificates, which simplifies the key management process. The research paper focuses on the problem of revocation in CLPKE, which is important for ensuring the security of communication, even in the presence of compromised or revoked keys. Revocation is particularly challenging in CLPKE because there is no certificate authority to revoke keys. The text then moves on to the issue of revoking traditional users from PKS constructions, which is traditionally done using CRLs but is not well suited to IDPKS, CBPKS, or CLPKS. Bonet and Franklin suggested a revocation solution to IDPKSs, where the KGC generates and sends new private keys to non-revoked users using secure channels, but this approach has a high computation burden. Boldredia et al. Proposed a revocable ID-based encryption scheme using a binary key structure, which reduces the key update size but has other limitations. Singh and Sai presented a revocation solution using a public key channel in IDPKS construction, where a user's full private key is divided into two components: a fixed initial secret key and a changed time update key, with KGC periodically sending new time updates. The text concludes by suggesting that there is much research to be done in this area and there are likely to be further developments and improvements to revocation mechanisms in the future. Now we will move on to the abstract of this research paper. So, the research paper proposes a new revocable CLPK scheme that overcomes the limitations of existing schemes and offers strong encryption security and practical efficiency. The main contributions of the study are the design and implementation of the new scheme as well as an analysis of its security and its efficiency. The abstract discusses the concept of a certificate-less public key system (CLPKS) and the need to address the revocation problem in existing CLPKS constructions. The authors proposed the first revocable certificate-less public key encryption (RCLPKE) and defined the new syntax and security notions of RCLPKE scheme. They also proposed a concrete RCLPKE scheme that retains efficiency for encryption and decryption procedures while providing an efficient revocation alternative using a public channel. The proposed scheme is based on a novel key update mechanism that enables efficient and secure revocation without relying on certificates. The scheme was implemented using the Charm library, which provides efficient and flexible support for pairing-based cryptography and evaluated through a rigorous analysis that is considered various types of attacks and performance metrics. The authors demonstrate that the RCL-PKE scheme is semantically secure against adaptive chosen ciphertext attacks under the computational and bilinear Diffie-Hellman assumptions. This indicates that the proposed RCL-PKE scheme is secure in practice, and the authors have demonstrated its security using established cryptographic assumptions. Overall, the abstract highlights the contributions of the paper, including the proposal of a new revocable certificateless public key encryption scheme that is both efficient and secure. The abstract also indicates that the paper addresses an important problem in existing CLPKS constructions, which is the need for efficient revocation alternatives. Now, let's move on to the problem statement. So, the problem statement is that the existing CLPKE schemes have limitations in security, efficiency, and scalability. Revocation is a challenging problem in CLPKE due to the absence of a certificate authority to revoke keys. Revocation is necessary to prevent compromised or revoked keys from being used to decrypt sensitive data. The research paper proposes a revocable CLPKE scheme that enables efficient and secure revocation without relying on certificates. So let's understand what this problem statement is. The problem statement on this slide highlights the limitations of existing CLPKE schemes in terms of security, efficiency, and scalability. Revocation is particularly challenging because CLPKE has no certificate authority to revoke keys, making it difficult to ensure that the compromised or revoked keys cannot be used to decrypt sensitive data. To address this issue, the research paper proposes a revocable CLPKE scheme that offers efficient and secure revocation without relying on certificates. The proposed scheme is designed to overcome the limitations of existing schemes and provide a strong security guarantees and practical efficiency. This is achieved through the use of advanced cryptographic techniques such as bilinear pairings, CDH and BDH assumptions, and a random oracle model. The paper concludes by suggesting that the proposed scheme is a significant step forward in the development of CLPKE schemes and highlights the need for further research to optimize the revocation cost, private key size, and encryption decryption cost. Furthermore, The lack of attention to the revocation problem in existing CLPKS constructions. This is a major issue. Without proper revocation mechanism, compromised or revoked keys can contribute to be used to decrypt sensitive data, undermining the security of the system. Therefore, this research paper's proposal of a revocable CLPKE scheme that allows for efficient and secure revocation is an important contribution to the field. The proposed scheme addresses the limitations of existing schemes and provides strong security guarantees and practical efficiency, making it a valuable addition to the available solutions for secure data encryption. So this was the problem statement. I hope you have clearly understood it. Now we'll be moving on to the methodology. So now we will be discussing the methodology. The methodology is a very important aspect of this research paper. So let's begin. The proposed RCL PKI scheme partitions a user's full private key into three components: an initial secret key, a time update key, and a secret value. The initial secret key is fixed and unchanged. The time update key is changed periodically, and the secret value is chosen by the user. Revocation is done by stopping the issuance of a new time update keys for revoked users, and the KGC periodically sends new time update keys to non-revoked users using a public channel, for example, an email. Existing PKS constructions such as IDPKS and RIDPKS suffer from the key escrow problem, as I have mentioned before, while CBPKS has a higher computational cost for encryption or decryption. All constructions except traditional PKS and CBPKS remove the need for certificates, and existing revocation solutions have limitations in scaling with the number of users. This RCL PKS construction is designed to provide an efficient revocation solution for existing CL PKS constructions. This RCL PKS introduces a new security model with the three types of adversaries. Type 1, which is the outside adversary. Type 2 is honest but curious KGC. And the type 3, which is the revoked user. The proposed RCL PKS scheme using bilinear pairings is provably secure against all three types of adversaries and is semantically secure against adaptive CCAs in the random oracle model. Performance comparisons demonstrate that the proposed RCL PKS scheme is efficient for encryption and decryption procedures and compared to existing CL PKS systems. So let's understand what this methodology is. So the entire proposed scheme is based on bilinear pairings in elliptical curves, which is a widely used technique in pairing based cryptography. The revocation method is based on a novel key update mechanism that enables the revocation of a user's private key without revealing the corresponding public key. So this is mentioned in this previous slide. This mechanism involves the use of a new parameter called the revocation tag, which is used to update the user's private key without changing the corresponding public key. This scheme is designed to be efficient in terms of computation and communication overhead, which is important for practical applications. So the proposed RCL scheme is now divided into three components: secret key, time update key, and a secret value. The initial secret key is unchanged. Time update key is changed periodically by the KGC, which is the key generation center. This is basically in this slide. And the next slide, we'll begin with the comparisons. I'll show you what the comparisons are. So comparison of traditional PKS, IDPKS RID-PKS, CBPKS, CLPKS, and RCL-PKS constructions. So what this does is that it averts the key escrow problem. Who can avert the key escrow problem? RCL-PKS, CBPKS, and CLPKS. The level of trust be placed on the key generation center. Traditional PKS, IDPKS, RIDPKS, and CBPKS place full trust on the key generation center or the KGC, while CLPKS and RCLPKS place partial trust. Next is the computational cost for encryption or decryption. What it tells us is that the RCLPKS and the CBPKS has a lower computational cost compared to the CLPKS. Next comparison is the required certificates and revocable functionality. RCL PKS does not require certificates, unlike the traditional PKS, IDPKS and RIDPKS, and offers revocable functionality like the RIDPKS. So basically, the article discusses different constructions of public key systems and proposes a new design concept called Revocable CLPKS or CLPKS. This aims to provide an efficient revocation solution for existing CLPKS constructions. In RCLPKS, which is the Revocable Certificateless Public Key System, a user's private key is partitioned into three components, namely what I have mentioned in this previous slide: initial secret key, time update key, and the secret value. The initial secret key and time update key are generated by the key generation center, and the secret value is chosen by the user. To revoke the users, the KGC simply stops issuing new time update keys for revoked users. Very simple. The KGC periodically generates new time update keys for non-revoked users and sends them to users using a public channel. The article compares RCL-PKS with other constructions in terms of averting the key escrow problem and the level of trust that is placed on the KGC, the computational cost for encryption and decryption. All these I have mentioned in the previous slide, which is here. I have mentioned all these comparisons before, so refer to them. Finally, I would like to conclude by saying that the article proposes a concrete RCL-PKE scheme using bilinear pairings. Bilinear pairings are very important in revocable certificateless public key systems. So, the article proposes a concrete RCL-PKE scheme using bilinear pairings, which is proven to be secure against different types of adversaries. All these three types of adversaries are proven by bilinear pairings, as I have mentioned in the PPT. Under the computational Diffie-Hellman CDH and the bilinear Diffie-Hellman, which is the BDH assumptions, the article demonstrates that the RCL-PKE scheme is semantically secure against adaptively chosen ciphertext attacks. What are these CCAs mentioned here? Are adaptive chosen ciphertext attacks. Finally, the article compares the performance of the proposed RCL-PKE scheme with previously proposed CL-PKE schemes. So this concludes the methodology that this paper has. Next, we will be moving on to the tools and technology used. Now we will see the tools and technologies used in revocable certificateless public key encryption systems. So let's begin. So an RCL-PKE is an 8-tuple of polynomial time algorithms. System setups, initial key extract, time key update, set secret value, set private key, set public key, encryption and decryption. Let's begin slowly. We'll first discuss system setup, then we'll move on to each of them and I will explain all of them slowly. So first is system setup. The algorithm takes a security parameter and the total number of time periods as input and returns a system secret key and public parameters. The public parameters are made publicly available for use by all other algorithms. Next thing we will discuss is initial key extract. This algorithm takes system secret key and a user's identity as input and returns the user's initial secret key. This secret key is securely transmitted to user. The next is the time key update. This algorithm takes system secret key and user's identity as input and returns the user's time update key for a given time period. This key is transmitted over a public channel. Next, we will be moving on to the set secret value. This algorithm takes an identity as input and returns that identity's secret value. The secret value is used to calculate the private key. So now we'll move on to the next phase, which is this. So first we will set public key. This algorithm takes an identity secret value as input and returns the corresponding public key. Very simple. Next, we take the set private key. This algorithm takes the user's initial secret key, time update key, and secret value as input and returns the user's private key. This particular key, the private key, is used for decryption. Next is encryption. This encryption takes an identity public key and a message as input and returns a ciphertext. This ciphertext can only be decrypted by user with a valid private key. And finally, decryption. The decryption algorithm takes a ciphertext and a user's private key as input and returns the decrypted message or a failure message if the decryption is not successful. So, to sum it all up, all these 8 steps, all these 8 tools and technologies, these algorithms work together to create a revocable certificateless public key encryption scheme. This scheme provides efficient and secure revocation without the need for certificates. This is how we will achieve that the need for. This is how we will achieve a secure and efficient revocation without any certificates. The scheme allows for the secure sharing of data among a group of users while also allowing the revocation of an individual user's access as needed. Now we will moving on to the final result and future score. So now we will discuss the result and the future score. RCL PKE scheme defined. This point is that the paper defines the framework for an RCL PKE scheme. Security notions. What the paper defines the framework for RCL PKE scheme and then formalizes security notions against different adversaries. Bilinear pairings. A concrete RCL PKE scheme using bilinear pairings is proposed and is demonstrated to be secure against the defined adversaries. Finally, revocable scalability challenge. Existing revocation solutions do not scale well for the KGC, but the proposed scheme offers a more efficient revocation solution. Future work would focus on reducing revocation cost, private key size, and encryption-decryption costs simultaneously. The security analysis showed that the proposed scheme is secure against various attacks, including adapted chosen ciphertext attacks, which we have seen earlier as the adaptive CCAs. The security guarantees were proven formally and backed up by simulation-based security analysis. The performance evaluation showed that the proposed scheme is efficient in terms of computation and communication overhead, particularly for large message sizes. The proposed scheme outperformed existing revocable CLPKE, which is the certificateless public key encryption schemes, in terms of computation and communication overhead. The results demonstrated that the proposed scheme is a viable solution for revocable CLPKE that offers strong security guarantees and practical efficiency. With that, we'll move on to the conclusion. In conclusion, the research paper Revocable Certificateless Public Key Encryption proposes a new revocable CLPK scheme that overcomes the limitations of existing schemes and offers strong security guarantees and practical efficiency. The proposed scheme is based on a novel key update mechanism that enables efficient and secure revocation without relying on certificates. Further, the scheme was implemented using Charm Library and evaluated through a rigorous analysis that considered various types of attacks and performance metrics. The results show that the proposed scheme is a viable solution for revocable CLE that offers strong security guarantees and practical efficiency. The research paper contributes to the advancement of secure communication technology by addressing the challenging problem of revocation in CLPKE. To summarize this paper, the paper proposed a revocable CLPKE scheme that addresses the limitations of existing schemes in terms of security, efficiency, and scalability. The security of the proposed scheme was analyzed and it was found to be secure against various attacks including adaptive chosen ciphertext attacks. This was demonstrated through formal security proofs and simulation-based security analysis. The performance of the proposed scheme was evaluated and it was found to be efficient in terms of communication and computation overhead, particularly for large message sizes. The proposed scheme outperformed existing revocable CLPKE schemes in terms of computation and communication overhead. This indicates that the proposed scheme is not only secure but is also practical. Very easy to understand. All this is that it is very practical, it is secure as well as appendable. Overall, the proposed scheme is a viable solution for revocable CLPK that offers strong security guarantees and practical efficiency. It has potential to address the limitations of existing schemes and provide a more efficient and secure solution for revocable CLPKE. With that, I would like to thank you. I hope you've understood this research paper deeply